Last time we took apart the smallest piece of a neural network. One neuron, two weights and a bias, three numbers, and we found out those three numbers are secretly a straight line. We also found exactly where that runs out. One neuron draws one line, and a line cannot bend. So today we fix that, and we watch a network find a shape nobody gave it. These 200 dots are the entire problem. 100 of them belong to one group. 100 belong to the other. Your eye has already solved it. Two curved bands, tangled together. So here is the part that should sound impossible. We are going to build something that finds that split by itself, and nobody is going to tell it the rule. No formula for the curve. No if statements. Nobody writes down where the boundary goes. This is the thing that has to figure it out. Two inputs on the left, 8 small units in the middle, one answer on the right. Every one of those 8 units is exactly the neuron from last time. Multiply, add, squash. 8 of them, side by side. Right now it has never seen anything. Its 33 numbers were picked at random. This is what it currently believes. That smear is its guess at where the split lives. It gets 34.5% of the dots right. 34.5%. A coin flip would beat it. 10 minutes from now, that exact same network, with nothing added to it, will be at 99.5%. Every step of how is what this video is. Start by following a single dot all the way through. This one, its position is -0.28 and 0.29. That is everything the network ever gets. 2 numbers. Each of those numbers travels down a wire into each of the 8 units in the middle. Every wire carries a weight. One number that decides how loudly this input gets heard over here. The unit multiplies what arrives by that weight, adds up everything it received, and squashes the total into the range -1 to 1. That is a neuron. That is genuinely all of it. Multiply, add, squash. 8 units, so 8 results. 0.07, -0.49, 0.38, and so on. Those 8 numbers go down 8 more weighted wires into the final unit, which does the identical trick one last time. And out comes one number between 0 and 1, 0.54. 0.54 is the network saying, I think this is group 1, but honestly, I am barely leaning. Nothing in there is clever. It is the same 3-step move you already know, done 9 times. And notice what has not happened yet. Nothing has learned anything. This is just arithmetic running forwards. The network has made a guess. It does not yet know it is a bad one. So the next question is the only one that matters. How do we tell it? The dot really is group 1. The correct answer was 1. It said 0.54, so it is off by 0.46. That gap is the only feedback this network will ever receive. Not advice, not an explanation, a number. Nobody tells it which weight was wrong. Nobody tells it what the answer should have looked like. It gets one number, and that is the whole conversation. Do that for all 200 dots and average how badly it missed, and you get a single score for how wrong the whole network currently is. 0.8444. That is the loss. Everything from here is one obsessive question, asked over and over. Which way do I move to make that number smaller? And that question has a shape. Let me show you the actual shape, because once you see it, the rest of this video is obvious. Pick any single one of the 33 numbers. Just one. Hold the other 32 perfectly still. Now drag that one number, and watch what the loss does. This curve is real. Every point on it is the network rerun over all 200 dots with that one weight set to that one value. This is not a diagram of an idea. It is a measurement. Right now that weight sits at -0.14 here. And the curve is going downhill to the right. Move the weight up, and the loss goes down. How steeply it goes downhill, at exactly this point, is a number, -0.244. That number is the slope. It is the whole of what a gradient is. A slope is not a direction on a map. It is an answer to one very small question. If I nudge this weight up a tiny bit, would the loss go up or down, and how fast? Negative slope means, push it up, the loss falls. Positive slope means, push it up, the loss rises. And the size tells you how much it matters. A steep slope means this weight is worth moving. A nearly flat one means it barely does anything. So now imagine that same curve, for every single one of the 33 numbers, 33 curves, 33 slopes. Get all 33 of those slopes, and you know exactly which way to move every number in the network, all at once. Which sounds like it should be enormously expensive. It is not, and the reason why is the best idea in this whole field. The answer came out too low. Something caused that. Some wires pushed it down harder than others. So the network walks backwards through the exact same wires, asking each one that same small question. It starts at the end, where it knows the error exactly, and works back one layer at a time. The error at the output tells it the slope for the 8 wires feeding the output. Those slopes then tell it the slopes for the 16 wires feeding those. Each step backwards reuses the work of the step before it. Nothing is computed twice. This wire has a steep slope. Change it, and the error moves a lot. This one is nearly flat. It barely matters. And notice, it never guesses. Each slope is calculated exactly, out of the same multiplications that produce the answer, just run in reverse. Running it in reverse is backpropagation. It is not a search. It is not trial and error. It is the chain rule, handing back a slope for every weight at once. One forward pass to make the guess. One backward pass to get all 33 slopes. That is the entire cost. This is the thing that made deep learning possible. Not the idea of learning from errors, which is old. The fact that you can get every slope in one sweep. Now the network edits itself. Every weight takes a small step in the direction that makes the error smaller. This one was minus 0.14. After a single step, it is minus 0.02. Weight minus learning rate times slope. That is the entire update. There is nothing else in it. Look at where it landed on the curve. Slightly to the right, slightly lower. That is one step downhill, and it is the only move this whole system ever makes. How big that step is a choice we make. Here it is 1/2, and that choice matters more than almost anything else. So let us actually test it. Same network, same starting numbers, same dots. The only thing changing is the step size. With a very small step, 0.01, it does learn. It just crawls. 400 steps later it is at 82%. With the step this video uses, 1/2, the same 400 steps get it to 89.5. Now watch what happens if we get greedy and set the step to 60. It does not learn faster. It throws itself so far past the answer that the loss climbs to 10.36, and it lands at 50%. A coin flip. Same network, same data, same starting point. Only the step size, and it went from working to destroyed. Too small, and it crawls. Too big, and it flings itself straight past the answer and never settles. One guess, one error, one set of slopes, one tiny nudge to every weight. That is one step of learning. So now watch what happens when we just do that, over and over. 5 steps in, and it has already jumped to 80.5%. The easy wins come almost immediately. Step 50, a straight edge has formed, and it is getting 88.5% of the dots right. And then it stalls. Watch the loss between step 50 and step 400. 350 steps of work, and it gains 1%. A straight line is the best a straight line can do, and these bands are curved. It is stuck at the edge of what it has worked out so far. This is worth sitting with, because it looks like failure. If you were watching this number and nothing else, you would think it was finished. But nothing here gives up, because the slopes never quite reach 0. It keeps going. And there it is. The boundary bends. Step 1200, 97.5%. Step 2000, lost 0.0273, 99.5%. Nobody ever told it that curve. It found it by being wrong 400,000 times and flinching in the right direction every time. But I owe you an explanation, because I have shown you that it bends without showing you how. A neuron is a line. We proved that last time. So how do 8 lines make a curve? Here they are. The 8 hidden units, drawn as what they actually are. 8 straight lines, each one cutting the space at its own angle. And each one has a weight saying how much it counts toward the final answer. Watch what happens as we switch them on one at a time. 1 unit, 75%. That is just a line, and it is doing about what a line can do. 2 units, 80. 3, 79. It goes down, because these were never tuned to work alone. They were tuned to work together. 4. 44.5. 5. 51.5. Still worse. Individually, most of them look useless. 6. 81. 7. 89.5. And the eighth, 99.5%. That is the whole trick. Not one clever unit. 8 ordinary straight lines, added up with the right weights, bending into a shape none of them could make alone. This network holds 33 numbers. The model you talked to today holds 175 billion or more. The loop is identical. Guess. Measure how wrong. Get every slope. Nudge everything a little. Repeat. Learning was never understanding. It is one number getting smaller, one flinch at a time. Next time we answer the question this video just raised. Adding more layers should make a network stronger, and for one specific reason, it does absolutely nothing at all. That reason is called nonlinearity, and it is the whole game.